Good morning everyone and welcome back. Today we are going to start a new unit of our Advanced Database Management System course. This is Unit 2, Database Recovery. Now before we get into the technical concepts, let's first understand why this topic is important. We know that a database is constantly being used to store, update and retrieve information. But what happens if something goes wrong while these operations are taking place? For example, there could be a system failure, a power failure, a software problem, or some other unexpected issue. In such situations, how can we make sure that our database remains correct and consistent? That is where database recovery comes into the picture. In this unit, we will start right from the basics. First, we will understand why database recovery is required and what different types of failures can occur in a database system. After that, we will learn about log-based recovery and understand how a database keeps track of changes so that it can recover when something goes wrong. Then we will grade in our notes, deferred update and immediate update. We will understand how each technique works, what happens when a failure occurs, and how the database is brought back to a consistent state. And finally, we will solve the numerical and case-based problems given in the lecture notes step by step. While solving these problems, I will focus more on explaining the logic behind each step so that you understand how to approach similar questions on your own. So while going through this unit, I would suggest one thing. Don't try to memorize everything from the beginning. First, focus on understanding the basic idea of recovery, why it is needed, and how the different techniques actually work. Once the logic is clear, the definitions, steps, and numerical problems will become much easier to understand. We will follow the content and sequence of the provided lecture notes throughout this unit, and we will cover each concept gradually. Database recovery.
Let us start with a very simple question. What exactly do we mean by database recovery? We all know that a database is used to store important information in an organized and safe manner. For example, we may have information about students, customers, employees, bank accounts, products, or transactions stored in a database. Normally, when we work with a database, we expect everything to happen smoothly. We expect the data to be stored correctly, transactions to complete properly, and the database to remain available whenever we need it. But in the real world, things do not always go as expected. Something can go wrong at any time. There could be a power failure, the computer or server might crash, a transaction might stop in the middle, the storage device could have a problem, or there could even be a software or human error. Now, when such a problem occurs, the database may be left in an incomplete or incorrect state. So what should we do in such a situation? We need some or incomplete state and bring it back to a correct and consistent state. And this process is what we call database recovery. In very simple words, database recovery means bringing a database back to a correct and consistent state after some kind of failure or problem occurs. Now let us understand why database recovery is actually necessary. Think about a very common example. Suppose you are making an online payment. You enter all the required details, you click on the payment button, and the transaction starts. But suddenly there is a power failure. The server crashes or Now let us understand why database recovery is actually necessary. Think about a very common example. Suppose you are making an online payment. You enter all the required details, you click on the payment button, and the transaction starts. But suddenly there is a power failure. The server crashes or the system stops responding. Now, what happens to the transaction? Did the payment actually go through? Was the amount deducted from your account? Was the transaction recorded in the database? What if the system updated one part of the transaction but stopped before completing the remaining part? These are very important questions. We cannot simply leave the database in the middle of a transaction. The database has to determine what changes should be kept and what changes should be removed. If the transaction was not completed successfully, the incomplete changes may need to be undone. On the other hand, if the transaction was successfully completed before the failure, the changes may need to be retained, becomes important. It helps the database handle failures and bring the system back to a proper and consistent state. Now, database recovery helps us in several important ways. First, it helps in restoring the database to an appropriate state after a failure. In some situations, data or changes may be affected, and recovery techniques help us restore the correct state of the database. Second, recovery helps in undoing incomplete or incorrect transactions. Suppose a transaction has started making changes, but because of a failure, it could not complete successfully. In such a case, the changes made by that incomplete transaction may need to be undone. And third, recovery helps maintain the correctness and consistency of the database.
This is probably the most important goal. Even when a failure occurs, we do not want the database to contain incorrect or contradictory information. So whenever you hear the term database recovery, try to remember these 3 basic ideas. Restore the correct state, undo incomplete or incorrect changes, and maintain database consistency. Understand the different recovery techniques that we are going to study in this unit.
Now, let us move to the next important question. What are the different types of failures that may require database recovery? We already understand that failures can happen for different reasons, but before we learn how recovery works, we need to understand what kinds of failures can actually occur in a database system. In our notes, we have 4 important types of failures. We will look at each one with a simple example. The first type is transaction failure. First, let us recall what a transaction means. A transaction is basically a task or a sequence of operations performed on the database. For example, adding a new record, deleting a record, updating information, or transferring money from one account. Now, imagine that a transaction has several operations to perform. It starts successfully, performs some of the operations, but before completing the remaining operations, something goes wrong. Maybe there is an error, or the transaction violates some condition, or the system stops the transaction. Now we have a problem. Some changes may already have been made, while the remaining changes have not been completed. So what should happen to the changes that have already been made? We cannot simply leave those changes as they are because the transaction was not completed successfully. The database may need to undo those changes and return to the previous consistent state. This situation is called transaction failure, and this is one of the situations where recovery becomes necessary. The second type of failure is system crash. A system crash can occur because of a power failure, operating system problem, hardware problem, or some other unexpected issue that causes the computer or database server to stop working. Let us take a simple example. Suppose several transactions are running on a database server. Suddenly, the power goes off and the server shuts down. Now, when the system stops, some transactions may have already completed successfully, while some may still be running. Some changes may have already been saved, while other changes may not have been saved. When the system starts again, the database cannot simply assume that everything is fine. It needs to examine what happened before the crash. Which transactions were completed? Which transactions were incomplete? Which changes should remain? And which changes need to be undone or performed again? The recovery mechanism helps the database answer these questions and restore the database to a correct and consistent state. This type of failure is known as a system crash. The third type is disk failure. We know that the database is ultimately stored on storage devices, such as disks. Now imagine that the storage device containing the database becomes damaged or fails. If the database information stored on that device becomes inaccessible or is damaged, the database system may not be able to use the data normally. This situation is called disk failure. In such cases, recovery mechanisms, along with appropriate backup and storage procedures, can help restore the database to an appropriate state. The fourth type is software or human errors. Not every database problem is caused by hardware. Sometimes the problem can be caused by software, or even by an incorrect action performed by a user. For example, a software bug may cause incorrect database operations. Similarly, a user might accidentally update or delete information that should not have been changed. In such situations, the database may need to recover from the incorrect changes and restore the appropriate state. So students, at this point, remember the 4 important types of failures that we have discussed: Transaction failure, system crash, disk failure, and software or human errors. These 4 categories will help us understand why different recovery mechanisms are required. Now, let us move to another very important question. Suppose a failure occurs. How does the database system know what happened before the failure? How does it know which operations were performed? How does it know which transaction was completed? And most importantly, how does it decide which changes need to be undone and which changes need to be applied again? For this purpose, the database system uses something called a log file. You can think of a log file as a kind of history or record of important database activities.
Whenever transactions perform important operations, information about those operations can be recorded in the log. The log can contain details that help the recovery system understand what happened before a failure. For example, suppose a transaction starts and performs some database operations. The recovery system keeps track of these operations through the log. If the transaction successfully completes, the system records that the transaction has committed. But what happens if the transaction fails? In that situation, the information stored in the log can help the recovery mechanism determine what changes need to be undone or what changes need to be applied again. So you can think of the log file as an important source of information for the recovery process. Now, there are two terms that we are going to use repeatedly throughout this unit. These are rollback and roll forward. Let us understand them in the simplest possible way. First, we have rollback. Rollback means undoing changes. Suppose a transaction makes some changes to the database, but before the transaction can complete successfully, it fails. If those changes should not remain in the database, the recovery system can undo them. So remember this simple rule. Rollback means undo. Now, what about roll forward? Roll forward means redoing or applying the required changes again. Suppose a transaction was completed successfully, but because of a failure, some of the required changes need to be applied again during the recovery process. The recovery system can use the available information to redo those changes. So our second simple rule is roll forward means redo. If you remember just these two relationships for now, you will already have a strong foundation for the problems we are going to solve later. Rollback means undo, roll forward means redo. We will come back to these two concepts again when we study log-based recovery, and especially when we start solving the numerical and case-based problems. At that point, you will see exactly how the log helps the system decide whether a transaction needs to be undone or redone. Now that we understand the different types of failures and the role of the log file, let us take a quick look at some of the common techniques used for database recovery. There are several recovery techniques that we may come across, such as log-based recovery, checkpointing, shadow paging, and backup and restore. Let us understand these very briefly. The first one is log-based recovery. As the name suggests, this technique uses a log file to keep track of the changes and activities performed by transactions. When a failure occurs, this information can be used to recover the database. The second technique is checkpointing. In checkpointing, the system periodically saves important information about the current state of the database. So instead of going through the entire history of transactions during recovery, the system can start from a suitable checkpoint. This can make the recovery process faster and easier. The third technique is shadow paging. In this technique, the system maintains information about an original version and a new version of the database pages. Changes are made to the appropriate pages, and when the transaction completes successfully, the new version can become the valid version. And the fourth technique is backup and restore. This is something we can easily relate to in our daily use of computers. We regularly create a backup copy of important data so that if the original data is lost or damaged, we can restore it from the backup. So these are some of the common recovery techniques. However, in this unit, our main focus will be on log-based recovery. And within log-based recovery, we are particularly interested in two important techniques: deferred update and immediate update. So now let us move to one of the most important topics of this unit, log-based recovery. Log-based recovery is a method used by the database management system to recover the database after a failure. We already know what a log is. A log is basically a record maintained by the DBMS that keeps track of important activities and changes performed by transactions. Think of it like a history of what the transactions have been doing. When a transaction performs an operation, the relevant information is recorded in the log. If everything goes well and the transaction completes successfully, the transaction can be committed. But suppose something goes wrong. Maybe the system crashes or the transaction fails in the middle. Now the DBMS needs to figure out what happened before the failure. This is where the log becomes extremely useful. Using the information available in the log, the recovery system can determine which transactions need to be undone and which changes may need to be redone. So whenever you hear the term log-based recovery, remember one simple idea. Keep a record of transaction activities so that the database can use that record to recover after a failure. Now, let us understand this process step by step. Suppose a transaction is running. It performs different operations on the database. At the same time, information about those operations is recorded in the log. Depending on the recovery technique being used, the actual changes may or may not be immediately written to the database. If everything goes well, the transaction completes and is committed. But suppose a failure occurs before the transaction completes. Now the recovery system looks at the log and tries to understand what happened. Which transaction was running? Which operations were performed? Was the transaction committed? Which changes were already applied? and which changes need to be undone or redone. The log provides the information needed to answer these questions. So the basic flow is quite simple. A transaction performs operations, important information about those operations is recorded in the log, and if a failure occurs, the log is used as a source of information for recovery. Keep this basic flow in mind because it will help us understand the numerical problems later.
Now, let us look at the structure of a log file. A log file contains different types of information about the operations performed by transactions. A log record can contain information such as the transaction ID, operation, item affected, old value, and new value. Let us understand each of these one by one. First, we have the transaction ID. The transaction ID tells us which transaction performed the operation. We normally represent transactions using names such as T1, T2, T3, and so on. For example, if we see T1 in the log, we know that the particular operation belongs to transaction T1. Next, we have the operation. The operation tells us what is happening with the transaction. It could be something such as start, read, write, commit, or abort. For example, start tells us that the transaction has started, while commit tells us that the transaction has completed successfully. Next is the item affected. This tells us which data item is involved in the operation. For example, the data item could be A, B, X, or Y. Now comes an important part, the old value and the new value. The old value tells us what the value of the data item was before the change. The new value tells us what the value became after the change. For example, suppose the value of A is initially 100, and a transaction changes it to 150. In that case, the old value is 100, and the new value is 150. This information becomes extremely useful during recovery, because the recovery system may need to either restore the old value or apply the new value again. So, when you look at a log record, try to identify these basic pieces of information. Which transaction, which operation, which data item, what was the old value, and what is the new value. Once we understand the structure of the log, we are ready to move to the two most important recovery techniques in this unit, deferred update and immediate update. Now, students, I want you to keep one very important question in your mind. When are the changes actually written to the database? This question is the key to understanding the difference between deferred update and immediate update. Let us put it very simply. In deferred update, the changes made by a transaction are not written to the actual database until the transaction successfully commits. In other words, the changes are delayed or deferred. On the other hand, in immediate update, the changes can be written to the actual database while the transaction is still running, even before it commits. And this difference is extremely important because it determines whether the recovery process may need to perform undo, redo, or both. So remember this basic comparison. Deferred update, changes are written to the database after commit. Immediate update, changes can be written before commit. Once this difference is clear, the concepts of undo and redo become much easier to understand. So let us first look carefully at deferred update. Deferred update is commonly remembered with a very useful rule. Deferred update means no undo, but redo may be required. Now, don't just memorize this statement. Let's understand why. Suppose the database currently contains A equals 100. Now, imagine that transaction T1 wants to change the value of A from 100 to 150. In the case of deferred update, the actual database is not changed immediately. The new value, 150, can be recorded in the log, but the actual database continues to contain A equals 100 until the transaction successfully commits. Now, imagine that T1 fails before commit. What happens? Since the actual database was never changed from 100 to 150, there is nothing to undo in the actual database. The database is still holding the original value, 100. That is the main reason why we say deferred update requires no undo before commit. Now, suppose instead that T1 successfully completes and commits. In that case, the new value, 150, needs to be reflected in the database. If the system crashes at an appropriate point during recovery, the information stored in the log can be used to redo the required changes. So the simple idea behind deferred update is before commit,
the actual database is not changed. If the transaction fails before commit, no undo is required. If the transaction commits successfully, redo may be required during recovery. This is why deferred update is commonly summarized as no undo but redo. Keep this rule in mind. In a little while, when we look at numerical and case-based problems, we will use this exact logic to decide what recovery action is required. Now, let us take this understanding of deferred update a step further. We have seen that during the transaction, the changes are kept in the log and the actual database is not updated immediately. The important point is that these changes become permanent only when the transaction successfully reaches the commit point. So the next question is, what exactly happens after commit? And how does the recovery system handle these committed changes if a system failure occurs? To understand this, let us continue with the role of redo during recovery and see how the log helps the system restore all the changes of successfully committed transactions. Suppose transaction T1 has performed its operations successfully and finally reaches the commit point. At this stage, the transaction is considered successfully completed, and its changes can be applied to the actual database. Now, imagine that after the transaction commits, the system crashes. When the system starts the recovery process, it may need to apply the committed changes again. In that situation, the recovery system can use the information stored in the log and perform redo. So let us make the rule very clear. If a crash occurs before commit, there is nothing to undo in deferred update because the actual database was not changed. If recovery is required for a transaction that has already committed, the recovery system can perform redo. And this is the reason we describe deferred update as no undo but redo. Now, let us look more closely at the log structure used in deferred update. Our notes show log entries such as tstart, tx, tx new value, tcommit, andtabort. The important thing to notice here is the information stored with an update. In deferred update, the update record mainly contains the new value. For example, suppose transaction T1 changes A from 100 to 150. The log records the transaction and the new value, 150. But remember, the actual database does not receive this change before commit. This is a very important point. The log knows what new value needs to be applied, but the actual database continues to contain the old value until the transaction successfully commits. We will soon compare this with immediate update, where the situation is quite different. Now, let us take the example given in our notes and work through it slowly. Initially, our database contains A equals 100 and B equals 200. Transaction T1 wants to perform two operations. The first operation is A equals A plus 50. So the initial value of A is 100, we add 50 to it. 100 plus 50 gives us 150. Therefore, after the operation, the new value calculated for A is 150. Now, the second operation is B equals B minus 100. The initial value of B is 200, we subtract 100. 200 minus 100 gives us 100. So the new value calculated for B is 100. Therefore, transaction T1 wants to change the database values from A equals 100, B equals 200, to A equals 150, B equals 100. Now, let us look at the deferred update log. The log contains information similar to start T1, then T1, A, 150, then T1, B, 100, and finally, commit T1. Now, stop here for a moment and notice something very important. We have calculated the new values of A and B. We know that A should become 150 and B should become 100. But because we are using deferred update, the actual database has not yet been changed before commit. So before commit, the actual database still contains A equals 100 and B equals 200. The log contains the information about the new values, but the actual database is still holding the original values. This is the basic idea behind deferred update. Now, suppose the system crashes before commit. What should we do? Let's reason through it carefully. T1 has not committed, and more importantly, the actual database has not been changed. Therefore, there is nothing to undo. We do not need to change A from 150 back to 100 because the actual database never became 150. Similarly, we do not need to change B from 100 back to 200 because the actual database never became 100. So in this situation, crash before commit, no undo. Now consider the other situation. Suppose T1 successfully reaches commit and then the system crashes. In this case, T1 is a committed transaction. During recovery, the system can look at the log and apply the required changes again. So the recovery process can perform redo. A becomes 150 and B becomes 100. Therefore, committed transaction, redo may be required. This gives us a very simple understanding of deferred update. Before commit, no actual database update. Crash before commit, no undo. Transaction committed, redo may be required during recovery.
Now, let us move to the second important recovery technique, immediate update. The basic difference is very simple. In immediate update, the changes made by a transaction can be written to the actual database before the transaction commits. And this one difference changes the recovery process significantly. Because the database may already contain changes made by a transaction that has not yet committed, the recovery system has to be prepared for both possibilities. It may need to perform undo, or it may need to perform redo. So remember this rule. Immediate update means undo or redo. Now, let us understand why undo may be required. Suppose the database initially contains A equals 100. Transaction T1 wants to change A to 150. Since we are using immediate update, the new value can be written to the actual database even before T1 commits. So the actual database may now contain A equals 150. But there is one important point. T1 has not yet committed. Now imagine that the system crashes before commit. What should happen? T1 did not complete successfully, but its change has already reached the database. Therefore, that incomplete change needs to be removed. The database needs to go back to its previous value. So A must change from 150 back to 100. This process of removing the incomplete change is called undo. So now you can clearly see why immediate update may require undo. The change was already written to the database before commit. Therefore, if the transaction fails, the recovery system has to reverse that change. Now, this also explains why immediate update stores both the old value and the new value in the log. Suppose the log tells us A changes from 100 to 150. Here, 100 is the old value and 150 is the new value. If T1 fails, the recovery system can look at the log and know exactly what value needs to be restored. It can take A from 150 back to 100. Therefore, the log structure for immediate update contains information such as start, transaction ID, data item, old value, new value, commit, or abort. The most important difference to remember is that the update record contains both the old value and the new value. Now, let us take the immediate update example from our notes. Again, the initial database values are A equals 100 and B equals 200. Transaction T1 performs A equals A plus 50. So A becomes 100 plus 50, which gives us 150. Then T1 performs B equals B minus 100. So B becomes 200 minus 100, which gives us 100. Therefore, the final values produced by the transaction are A equals 150 and B equals 100. Now, look at the immediate update log. We have start T1, then T1, A, 100, 150, and T1, B, 200, 100, and finally, commit T1. Now, notice the difference from deferred update. For A, the log contains both 100 and 150. The 100 is the old value, the 150 is the new value. Similarly, for B, 200 is the old value, and 100 is the new value. This information is extremely important during recovery. Now, suppose the system crashes before commit. Because this is immediate update, the new values may already have been written to the actual database. Therefore, we need to perform undo. For A, the log tells us old value equals 100, new value equals 150. So during undo, we restore A to 100. For B, the log tells us old value equals 200, new value equals 100. So during undo, we restore B to 200. Therefore, after recovery, the database returns to A equals 100 and B equals 200. This is exactly what we expect because T1 did not successfully commit. Now, let us consider the other possibility. Suppose T1 has already completed successfully and reached commit, and then the system crashes. In this situation, T1 is a committed transaction. During recovery, the system can use the log to redo the changes. So A becomes 150 and B becomes 100.
Therefore, after recovery, A equals 150 and B equals 100. So in immediate update, depending on where the failure occurs, we may need either undo or redo. And this is why we summarize immediate update as undo or redo. Now, let us compare deferred update and immediate update carefully. The first difference is when the changes are written to the actual database. In deferred update, the changes are applied to the actual database after the transaction commits. In immediate update, the changes can be written to the actual database while the transaction is still running. The second difference is undo. In deferred update, undo is not required for a transaction that fails before commit because the actual database has not been changed. In immediate update, undo may be required because the changes may already have reached the actual database before commit. The third difference is the information stored in the log. In deferred update, the update record contains the new value. In immediate update, the update record contains both the old value and the new value. So there is a simple way to remember the entire difference. For deferred update, think of the process like this. The transaction starts, the updates are recorded in the log, the actual database remains unchanged. The transaction commits, then the changes are applied to the database. If a crash occurs before commit, there is nothing to undo. If recovery is required for a committed transaction, the changes can be redone. Now, for immediate update, think of the process this way. The transaction starts, the updates are recorded in the log, the updates may also be written to the actual database, then the transaction commits. If a crash occurs before commit, the changes may need to be undone. If the transaction has already committed, the changes may need to be redone during recovery. So the key difference is actually quite simple. Deferred update delays the database update. Immediate update allows the database update immediately. And because of this difference, their requirements are different. Now, students, before we move toward the numerical problems, I want you to remember one very important idea. Deferred update means no undo but redo, and immediate update means undo or redo. But please don't just memorize these two statements. Try to understand why. In deferred update, there is no undo because the actual database has not been changed before commit. In immediate update, undo may be necessary because the changes may already have reached the database before commit. And both techniques may require redo when committed changes need to be applied again during recovery. Once this logic is clear, the numerical problems become much easier. So now we are ready to move into the most important application part of this unit, numerical and case-based problems on database recovery. In these problems, we will work with transactions such as T1, T2, T3, and so on. We will start with the initial database values. Then we will follow every operation performed by each transaction. We will calculate the new values carefully. We will identify the right operations. We will check whether a transaction has reached commit. And then we will carefully identify the exact point at which the system crash occurs. Once we know all of this, we can decide whether the recovery process requires undo or redo. Finally, we will calculate the database state after recovery. Now, one important thing. When we solve these problems, we are not going to simply look at the final answer. We will solve each problem step by step, just as we would solve it on the classroom board. For every problem, we will first identify the initial values. Then we will follow the transaction operations one by one. Next, we will calculate every changed value. After that, we will check the commit or abort status. Then we will identify the crash point. And finally, we will decide whether to perform undo or redo and determine the final state of the database. This approach will help you understand the actual logic behind database recovery, rather than simply memorizing the answers. So, with the basic concepts now clear, let's move to the numerical problems on deferred update and immediate update. We will start with a simple problem and gradually move toward problems involving multiple transactions and different crash situations. Take your time with each step because the key to solving these problems is not speed. The key is to carefully track the transaction, the values, the commit status, and the point of failure. So, let's begin with our first numerical problem.